Good afternoon. I want to thank the organizers of this conference, and especially Mr. Woods, for the recognition of the power of future concepts, especially when they can be started now. Today, I will present the status of the modern day space elevator with these key points. Space elevators have begun engineering development. We have the material coming out of the lab. Space elevators are the green road to space by using electricity to raise to geosynchronous. Space elevators are the permanent infrastructure, which leads to daily, routine, safe, and inexpensive delivery. They deliver massive cargoes to geo. Can you believe 170,000 tons per year? Delivery statistics are excellent, 70% to geosynchronous from the mass on the pad. These characteristics will enable dreams of many, such as the space solar power. Two further points are necessary. Space elevators are the simple, elegant solution to the rocket equation because we avoid it. The strategy is to have a cooperative, compatible relationship with advanced rockets. We call that dual space access architecture, leveraging the strengths of both. But first, I want to recognize Arthur's presentation and his emphasis on Cassiopeia. Marvelous. My presentation is based on Dr. Mankin's approach, both of which have common goals and approaches leading to a carbon-free Earth environment. My conclusions are based on mass to orbit or geosynchronous, not specific programs. So please recognize that both Ian Cash and John Mankins are correct, and I encourage them to accelerate the programs toward a better world. Our process is called dual space access architecture, where we're going to enable the combination of both rocket strengths and space elevator strengths working together. Rockets have tremendous strengths. They're there today. They lift a lot of mass to different orbits. They move people through radiation belts very rapidly. Space elevators have tremendous strengths with their infrastructure capability, daily routine, etc. They're also the green road to space. They lift things with electricity. So the combination of the strengths is really where it's at. Space elevator is simple, 100,000 kilometer, 1 meter wide tether, rotating around the Earth with a large mass at the end, providing that tension outward with centrifugal force. So we have a straightforward concept, simple, 7.76 kilometers at the tip. That's really fast. We can get to Mars in 61 days. And oh, by the way, we can release toward Mars every day of the year. There's no 26-month wait. It's a simple solution because we avoid the rocket equation. The concept is two tethers together in what we call a galactic harbor. The reason we have that is one up, one down, one principal, one backup, or two up just to make a lot of profit. But two systems, and I like to think we have the second one, so we're never captured by gravity again. We have a green road to space. We published a report on that, a little more on that later. And we can deliver 30,000 tons per year in the first real operations. The concept is three major regions, the apex anchor, the geo region. Obviously, the geo region will be worked hard because it's a natural location for spacecraft, productive spacecraft. And then the Earth port. And the Earth port will be about 80 kilometers or 40 kilometers between the two tethers. And it's a very straightforward system. The characteristics I talked about a little earlier, but basically train tracks or a bridge across a river. It's permanent infrastructure, 24/7, 365, 50 years. It's a massive undertaking, but it beats the gravity well in an environmentally friendly manner. Here's a Green Road to Space report. It's on our website. You go there, you can download it free PDF. It essentially says that we can raise things with electricity and not impact the atmosphere nor low Earth orbit with any spare parts left over. We can also do massive movement to orbit, the geosynchronous and beyond. Here's our concept. 3 galactic harbors, 2 space elevators in each. They would be created by competition, government to government, commercial to commercial, corporation to corporation. We're going to have multiple ones because the capability is so awesome that people will need it. 7 climbers a week per space elevator, 2 elevators per galactic harbor, 14 metric tons per payload. That's the payload, 6 metric tons for the climber. So we can do 25,000 tons in the first year. And then the chart on the right shows the annual growth up to over 170,000 tons per year to geosynchronous and beyond. When space elevators, why not both? Well, of course, if we have a space elevator, we ought to leverage the strengths of advanced rockets, reusability, inexpensive, beautiful lifts, massive stuff to orbit. That's really, really great. We need to do that. They do have a slight problem of 2% delivery statistic. We'll get into that in a few minutes. Space elevators are green and operational will be continuous. So the problem is we're not there yet. 2036, 2038, something like that. The example we're going to use is space solar power. The projected need for space for total electricity around the globe is 5,000 gigawatts. Now, much of that will be done by solar and wind and all that kind of stuff. But what we have to do is get rid of coal power plants. So what we need to do is replace a lot of the current capability with space solar power inputs. We're estimating, I should say, John Mankins, a whole bunch of other people, are estimating that we need 12% of that 5,000 gigawatts done from space. That would be 600 gigawatts. If we take an example, Phoenix, I live in Phoenix, so it's always natural to do that. We say we need basically one satellite, one Mark IIA, to satisfy the needs, the extra needs beyond what we have today, and to replace coal plants. One satellite. Well, one satellite looks like this. It's an Alpha Mark II, 2 gigawatts of continuous power down to Phoenix. That would be excellent. We have a 9,200 tons to get to geosynchronous to assemble it to make it one satellite. If we were going to launch 20 tons per rocket, which is what they do to geosynchronous, 20 tons per, that's 460 launches just for one of the satellites. And that's only 2 gigawatts. We need 600 gigawatts. So that's 300 times that. So it's 300 satellites we need. Here's an example we used in our report. Basically, we need that orange line. That's 12% of the needs for electricity around the globe in 2060. So if we provide space elevators going into effect about 2036, 2038, we start putting up mass to geosynchronous very rapidly, and we can meet the needs of humanity. In fact, we can exceed it in time and almost approach the top line, which is 1/4 of all energy needed by the human race. So the space elevator can provide space solar power satellites to geosynchronous, enabling our need. This is a chart that then adds what rockets can do. At 20 metric tons per launch to geosynchronous, we're talking about that red line, but that's 1,000 launches per year at 20 metric tons per launch vehicle. That's 3 a day going to geosynchronous. And then they don't even get to half of what we can provide, significantly short of what we really need for humanity's reach in 2060. Here are the numbers for rockets. 600 gigawatts needed, 2 gigawatts per satellite at 9,000 tons each. If we use starships at 20 tons to geo per launch times 1,000 launches a year, it's 138 years. Bummer. Why is that? Because the rocket equation is so lousy. You eat up your seed corn, so to speak. You've got this Apollo 11 on the right. We have a little capsule there. It provided 0.5% of the mass that was on the pad to the surface of the moon. So think Mars, 0.5% of the mass on the pad on the Earth will get to the surface of the moon. I mean, Mars, surface of Mars. The delivery statistics are poor with rockets. That's the conundrum. Why do we use stinking rockets when we can only get 2% to geosynchronous and beyond? The answer is it's the only way. We need to move up and have an evolutionary step, add space elevators. They can put 70% to geosynchronous. Here's a little picture with numbers. The astronaut capsule that got back to the surface of the Earth was less than 2/10 of the mass. So to return astronauts is also very tough. There's some Atlas numbers. Here's a whole bunch of other numbers. You notice none of them are at 2%. 2% is gracious. Oh, and then here's our guys that went to Mars this last year or so. 0.5% got there. Ooh, that's not very good. And then there's some other numbers. Those are also not very good. So the real kicker is we need to have the strengths of rockets and the strengths of space elevators combined and have a dual capability. Rockets to open up the moon and Mars and space solar power, space elevators to then move the massive stuff to get there. Here's an example where the rockets will provide the prototypes in low Earth orbit, and then the prototypes of geosynchronous and the test vehicles. And then you start putting up the mass to do more than one satellite. That's when space elevators can come in like 2036. And we can provide that for them downstream. Massive movement, there's the chart showing 22,000 tons is all humanity is put into orbit. And by the way, that was low Earth orbit, so you got to multiply or divide by 2 to get to geo. And the flow of mass on the right. Permanent space infrastructure, sooner than you think. Definitely, we can do it. We're in the process. We've started the development. The result is if we can combine rockets and space elevators, we can fulfill many dreams. Here's the dream of space elevators, the green road to space. 6 of them around the equator, moving a lot of mass. But why are we doing space elevators? The answer is humanity demands that we have dreams. And to reach those dreams, we need to move massive amounts of cargo to geo and beyond. To do that, we need an evolutionary step to space elevators. So space elevators are the simple, elegant solution to the rocket equation. They avoid it. Thank you very much.